So now we try to find the characteristic function for this case here. In the previous video, we found out that the characteristic function for s of t minus s is given by this expression. And, oh wait, did I forget to write the sum here somewhere? No, it's just because I shouldn't have a k up here. I apologize for that. I forgot to remove the k after summing up to the exponential expression. So there's an error in the previous video, just so you know. Okay, so now we want to find this thing here, and we want to show that it's the same as this expression that we found earlier. So let's just start calculating and see what happens. So the mean value of e to the ix, that's s to t, is equal to, well, by definition, what we actually have is e to the ix s of t minus s of s, right? And that is equal to the mean of e to the ix, and then I have the sum, and now I'll add from j, equals to n of s plus 1. So I've removed the n of s first terms because I subtracted s of s, up to n of t of xi. And since we're already here, let's just also do the conditional expectation part. So we condition on n and take the mean value. So we do the double expectation again. This is a trick that we will use again and again. So now the question is, like, what exactly should we condition on? Should we condition on n of t? Should we condition on n of s? Should we condition on both? What should we condition on? Well, the thing is, actually we can just try and see whatever works, right? So let's just try to experiment a little bit more here. So while we're doing these conditioning exercises, we'll move further and further away from what you knew before. And so let's just experiment a little bit. Let's condition on n of s and n of t. There isn't enough space here. So if I just condition on n of s and n of t, then I think we'll be pretty safe. And if we need some independent increment property later on, then we can just turn one of them into the increment n of s to t. But we haven't seen that we need that just yet, so let's just try and wait and see. Okay, so this is equal to, let's just try to compute the values here. So I have the sum for k equals 0 to infinity, and then I have another sum for m equals 0 to infinity, and the probability that n of s is equal to m, and whoop, now we kind of have a problem, because if I want to do this properly, I'll actually have to say that I look at the n of t's that are greater than n, because n of t has to be greater than n of s, and that's just not fun to play with. So again, we will go back and say, instead of looking at n of t, we will look at the increment from s to t. So that n of s to t is equal to k. And then what do we have? Then we have the mean of the exponential of ix n of s plus 1 up until n of t, xi given n of s is equal to m, and n of s to t is equal to k. So this is a rather long expression. What can we do now? Well, we can just write up the definition of this conditional expectation here. Put everything out there. So first we have this probability. And this conditional expectation, how do we do it? Well, we divide by the probability of whatever we condition on, if we have an event here. So we divide by the probability of this occurring. And then we write up, I think I need a parenthesis here, and then we write up the mean of this thing restricted to, the mean of, we write up the mean of this thing here restricted to whatever we condition on. So the mean value of the exponential of xi, for I going from, sorry, so j here, for j going from n of s plus 1 up to n of t, and conditioned on the fact that n of s is equal to m, no, not conditioned on, restricted to the event that n of s is equal to m, and n of s comma t is equal to k. Okay, good. So first of all, these two cancel out. And then what do we have? Well, again, I can use the fact that since I'm looking at the restriction of the exponential of the x's on the set where n of s is equal to m and the increment from s to t is equal to k, then essentially the n of s and n of t in the sum boundaries cannot be anything other than respectively, well, other than respectively m plus 1, and on the top m, which is the value that n of s attains, plus k, which is the increment from time s to t. Okay. And then, of course, I have to multiply by this indicator function that comes afterwards here. I have to multiply by the indicator function, but since we know that the xi and the n's are independent, I can just move out the n's. So I have the mean value of the indicator function of the n's here. Okay, and this is a very nice feeling because what I can do now is I can also, well, let's just take it one step at a time. The mean of an indicator function is equal to the probability of whatever the indicator indicates. So I actually have first and foremost, I have the probability that n of s is equal to m. And then, because of independent increments, I also have the probability that n of s comma t is equal to k. And then we multiply on this thing here. And now look, I'm summing k terms. I'm summing k terms from m plus 1 to m plus k. But since I'm summing k IID terms, I can also just start my sum from 1 and then let it go up to k, right? Because the xj's are IID. And then the last step is to notice that this thing only depends on m, and I can move it outside of the sum with the k's, and after that it will sum to 1 because it is a sum of point probabilities. So what I have left now is the sum k equals to 0 up to infinity of the probability that the increment in claim count from time s to t is equal to k, multiplied by the mean value of this thing here. Okay, so let's just look at where we wanted to arrive. We wanted to arrive here, right? We want something with t minus s. And for that, we can think a little bit about our assumptions. We assume that we have a homogeneous Poisson process. And since we assume we have a homogeneous Poisson process, well, what does that mean? That means that the increment from time s to t in the Poisson process has the same distribution as the increment from time 0 to t minus s. Hence, we can rewrite the above probability to this. Okay, so actually, essentially now we are actually done, because when we were calculating the characteristic function of s of t minus s earlier, we also arrived at this step, and then we just finished it off by doing the last calculation. So we have already shown now that this is equal to the characteristic function of s of t minus s. But I mean, we can just finish it off anyways and conclude in exactly the same way as we did in the earlier case, that this is equal to e to the minus lambda t minus s multiplied by 1 minus the mean of e to the I x1 as such. And in conclusion, this is equal to the characteristic function of e to the I x s. Okay, so now we're actually done with A. We also have B. But actually, B kind of works using the same principles. So what I would like you guys to do before I release the solution of B is for you guys to kind of try to look at B and try to solve it on your own first. Just try to apply the same techniques and see what happens. And see what happens. Yes? Okay.